Hello everyone. In this session, I am going to discuss about sorting algorithms. Those are quicksort, merge sort, and radix sort. So let's begin our session. What is quicksort? In a level computer science, a quicksort is another example of a divide and conquer algorithm that reduces the size of the problem into smaller problems that are more easily solvable by an algorithm. So I'm going to explain about with a small example. Let's take an array having the elements 8, 2, 4, 8, 2, 6, 1, 7, 9, 1, 4. Initially, we have to take one element as pivot element. Either you can take first element as pivot element or the last element as pivot element or any one of the element or middle of the array. Middle element in the array, you can take it as pivot element. But it's not a rule that you can take any element from the array as pivot element. First, initially, I am considering the first element as pivot element, that is P. The first element 8 I am considering as pivot element. And next we are going to use two pointers. Those are left and right. I am denoting as L and R, where L is a pointer which we set next to the pivot element. Next to the pivot element, pivot plus 1 I used to set as left pointer, and the last element in the array that pointed by the right pointer, that is R. Okay, first element as L and the last next to the pivot element as L and the last element as R. These are two pointers. Okay, so first what we will do is we have to increment the left pointer until you get a greater value than pivot element. You have to increment left pointer one by one until you get a greater value than pivot element. And we have to decrement R one by one until you get a lesser value than pivot elements. Okay, set the pivot element to the first value, set left pointer to pivot plus 1 and set right pointer to the end of the list. Then increment left until array of left is greater than the pivot. Now the pivot element is 8. Now you start incrementing by 1. First you check whether 2 is greater than 8. No. Then what you have to do as per our rule, you have to increment the left pointer until you get a greater value than pivot. Then the left pointer will be here. Okay. Now, what is the value? 6. Is 6 greater than 8? No. False. Again increment left pointer by 1. Left pointer will be here now. The value which is pointing by a left pointer is 1. Is 1 greater than 8? No. Then you increment again. Left pointer will be here now. Is 7 greater than 8? No. Again you increment. Is 9 greater than 8? No. Yes. Is 9 greater than 8? Yes. Now you stop incrementing. Then decrement the right pointer by 1 until you get a lesser value. First you start with R. What is the value which is pointing to R? 4. Is 4 less than 8? Yes, true. If it is true, you need not decrement. So now here left is pointing to 9 and the right is pointing to 4. If L is less than R, let's say the indexes are 0, 1, 2 and 3, 4, 5, 6, 7, 8. Is 6 less than 8 positional values? Yes. If it is yes, you have to swap. If it is yes, we have to swap. See here, L is pointing to 9 and R is pointing to R is pointing to 4. Now, the positional values of these are 0, 1, 2, 3, 4, 5. Right. It is 5. And it is 7. Yes, 5 is less than 7. L is less than R. If L is less than R, swap. Swap the elements. See, 4 and 9, you swap. Then you will swap left and right, you will get this array. You'll get this array. Now, again, continue the procedure. Continue with step 2 to 4. 2 to 4, what are the 2 to 4s? Increment left to get a greater value, decrement right to get a smaller value. Then what happens? What happens here? Now again you increment left by 1. So left will be is left increment by 1. So here the left value will be is 1 greater than 8? No. Then you increment left again. Left will be here. Left will be here. Is 9 greater than 8? Yes. If yes, you stop incrementing left pointer. Then decrement the right pointer. Decrement the right pointer by 1 to get a smaller value. 1. Is 1 less than 8? Yes. Stop the procedure. Now the right pointer is here. Current right pointer. Left pointer is here. This position is 6 and this position is 7. Is 6 less than 7? No. Is 7 less than 6? Left less than R. Is 7 less than 6? Is left less than R? No. If no, what you have to do is you have to swap the right point's value. Right is pointing to 1, right? So swap the right value with pivot element. Then what happens here? Swap the right value means right is here, right? Right is, check this. Right is pointing here. This and this you have to swap. Okay. Then it makes this array. Now you should understand one is sorted. One is at correct position. Now recursively call the function call on all items. This is sorted. This item is sorted and this will make an array and the remaining elements will be another array. Recursively call the function on all items below the pivot and all items above the R are. So where is your pivot element? Here, right? All elements are below the pivot element and all elements, these are above the pivot element. So now this element has been its correct position. Okay. Same. Again, you continue the same procedure to sort individual arrays again. We will divide a complex problem into smaller ones. Now see here, the array, this will be a subarray. From here to here one array and 9 is another array. 8 is sorted element. Same again, you start the procedure, take first element as pivot element and the next two pivot element as L and the last element as R. Now you start incrementing L until you get a greater value than L. Is 2 greater than 1? Yes, true. You stop incrementing L and you decrement R by 1 to get a lesser value than pivot element. Is 4 less than 1? No. Is 7 less than 1? No. Is 1 less than 1? No. And is 6 less than 1? No. Is 2 less than 1? No. Is 1 less than 1? No. There are no more elements in the array. Now the pointer, R pointer is here and L is here. Now you check. Is L less than R? What is the position of L? 1. What is the position of L? 1. And what is the position of R? So this is not satisfied. When this is not satisfied, you have to swap the right element with the pivot element. Right element with the pivot element. Now 1 is sorted. Okay. 1 is sorted. It is at correct place. Same. Similarly, you follow remaining elements. This will become another subarray. Okay, left pointer does not move as greater than 1. So this will become the another subarray. 2, 6, 1 and 7, 4. Now again you take this element as pivot element and the next element as left pointer and the next element, the last element as right pointer. Same. Start, continue the procedure. Increment left pointer by 1 to get a greater value. Yes, the next element is greater than, yes, 6 is greater than 2. Stop incrementing. And is 4 less than 2? No. 7 less than 2? No. And 1 less than 2? Yes. Yes. If yes, here the right pointer. Now is L less than R? What is the value of L? 0, 1, 2. Is 1 less than 2? Yes. If yes, what you have to do? You have to swap the values. You have to swap 6 and 1. So it will become 1 and 6 here. See here. Check here, 1 and 6. Again, continue the procedure. Start incrementing left by 1 to get a greater value. Is 6 greater than 2? Yes. Stop incrementing and decrement R by 1. Is 1 less than 2? Is 1 less than 2? Yes. Stop the procedure. But now the value of L is 2. R is 1. Is 2 less than 1? No. When it is not less than 1, what we have to do? We have to swap with right and pivot elements so that it will become 1, 2, 6, 7, 4. Now this 1 is at correct place now again. You have to sort this remaining array. Okay. 1 is already sorted, 1, and in the next iteration 2 will be sorted, then 6, 7, 4. So similarly 6, 7, 4 will be sorted, 8, 9. This is how we compute sorting algorithm. So I'll explain once again with here itself. Let's say you will be having the elements same 8, 2, 6, sorry, 8, 2, 6, 1, 7, 9, 1, 4. So first element you consider it as pivot element and next to pivot element as L and the last element as R. So you have to increment one by one. Is 2 greater than 8? No. Is 6 greater than 8? No. Is 1 greater than 8? No. Is 7 greater than 8? No. Is 9 greater than 8? Yes. Now you stop the procedure. L points to here. And R you have to decrement to get a smaller value than pivot element. Is 4 less than 8? Yes. Now you check the condition. Is left less than R? Yes, true. Left is less than R. So when left is less than R, you have to swap this. Okay. So then your array will be 2 sub 6 1 7 4 1 9. But the left points to now 4 and right points to 9. Same, continue the same procedure again. Increment left by 1 to get a greater value. No. Is 1 greater than 8? No. Yes. 9 is greater than 8. Then you decrement R by 1 to get a smaller value. So R will be here, 1 less than 8. Now what is the value of L? L is 7 and R is 6. Positional values. 7 is not less than 6. When it is not less than 6, you have to swap 8 with pivot element, R with pivot element. So 8 will come here and 1 will be here. Okay. So 1, 2, 6, 1, 6, 1, again 7, 4. Here the 8 will be and 9. Now you should understand that left side of the pivot element is less than and right side of the pivot element is greater than. Similarly, you apply for this array, and this is anyway one element, it is sorted. Again, this element as pivot, do that, continue the process. Okay, this is merge sort algorithm, and this is quick sort algorithm, sorry. The time complexity of quicksort algorithm is, it is a divide and conquer algorithm, which means the problem is reduced, creating an easier problem to solve. The complexity of this algorithm is order of n when there are n list of items. Okay, and space complexity is order of n. Next sorting algorithm is merge sort. Merge sort is an example of divide and conquer algorithm that reduces the size of the problem into smaller problems similar to quicksort algorithm that are more easily solvable by an algorithm. Especially the merge sort divides the list in half, creating two sublists. Each sublist is then divided into until each sublist contain only one item. Okay, element group or one item or one element. Groups of two sublists are then sorted and merged again. Okay, see how it happens here. Let's say I'll be having an elements 15, 5, 2, 7, 4, 9, 10, 1, 8, 3. How many number of elements are there? 3, 6, 9, 10 elements are there. Then these 10 elements will be divided into 5 elements each. Means, let's say your array size n is equals to 10, then 10 by 2, 5, right? So up to, let's say the positions are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up to 5 it will be divided into one array, and 9, this 6 to 10 will be another array. Okay, 15, 5, 2, 7, 4, and another subarray is 9, 10, 1, 8, 3. Similarly, again, the subarray contains 5 elements. Again, 5 by 2. 5 by 2 means 2 to the 4. So 15, 5 as one array and 2, 7, 4 as another array. Similarly here, 9, 10 as one subarray and 1, 8, 3 as one another subarray. This is how we divide into sublist. Then there are only two elements in this here. So 2 will be 2 by 2 because you have to divide into two halves until you get one value or one element, as I said, 15 and 5. Here you will be having three elements. So 3 by 2 is equals to 1 integer value. So 1 and remaining here. Okay. And here you will be having two elements, 1, 1 each, and three elements, 3 by 2. 3 by 2 means 1. So that it will be divided into two halves. One array will be start, and it will continue till mid. Okay, mid means only one. Another array will be, it starts from mid plus 1 to end. Okay, means here start is 1, so 1, mid value anyway 3 by 2 1, so that it will be 1 only. Here remaining element mid plus 1 is 8 till the end of the array 3. Okay, now few more elements, because we have to divide into smaller subarrays until you get a one element. 15, 5 are one elements and 2 is also one element, but 7, 4 again there are two elements. This you have to divide into 1, 1 each, and 8, 3 also. So now you got all elements are individually sorted. Okay, all lists are individually sorted. You have to merge these lists, and while merging into one list, See here, 15 is sorted as individually in this list and 5 also sorted individually in this. When you merge into one, you have to sort. You compare with the another list of items and then merge as a one list. So 5, 15. Similarly, 2, 7, 4, 9, 1, 10, 1 will become, when you merge, 1, 10, 8, 3, because while merging itself you have to sort. Then these sublist you have to merge into another here, this also. Okay, these two sublist you have to merge into one. You have to compare with the first. Is 5 less than is 5 great less than 2? No, then 2 should come here. Okay, because it is sorted and it is sorted. And compare again, is 5 less than 7? No, right? So 7 will be here. So now you compare 7 and 15. 7, 15. This is how you have to sort while merging itself. Then it will form 2, 5, 17, 15, 7, 15, and 1, 4, 9, 10, 3, 8. Okay, and then again you merge into one list. So this is how while adding itself, while merging, you have to sort and you have to frame a single array. Divide into smaller problems, divided into sublist, and the sublist, while merging into one list, you have to sort and add it. This is how we will perform merge sort. But notice that having the list sometimes produces odd number of elements in the sublist. But you have to see, let's say if it is 9, let's say the number of elements are 9, you have to take the integer. Okay, 4. So that 1 to 4 will be one sublist and 5 to 1 will be 5 to 9 will be another sublist. Okay, and in order to merge two sublists, 2 pointers are required, one for each sublist, and the time complexity of this algorithm is order of n, and space complexity of this algorithm is order of n log n is time complexity. Worst cases, best cases, order of log n. Space complexity is order of n. And the next algorithm is radix sort. Radix sort algorithm, whereas another will take n iterations. But radix sort is linear sorting algorithm that sorts elements by processing them digit by digit. Here digit by digit elements will be sorted, and it is an efficient sorting algorithm for integers or strings with fixed size keys. And rather than comparing elements directly, Radix sort distributes the elements into buckets where we will be having 0 to 9 buckets. Let's say it will be dropped into the digits, or the numbers will be dropped into these buckets. By repeating sorting the elements by their significant bits from the least significant bit to most significant bit, Radix sort achieves the final sorted order. And the Radix sort algorithm we use place value. The concept of place value plays important role. Place value, as you know already, I hope. Let's say 231. 1 is at units place, 10 is at tens place, 2 at hundreds place, right? Based on the place value, Radix sort idea is dependent. It assumes that sorting numbers digit by digit will eventually result in a fully sorted list. Radix sort can be performed using different variations such as least significant digit and most significant digits, or MSB, MSB, most significant bit, and least significant bit. This bit you can tell as digit. Okay, how does it will work? Let's say we have elements these 170, 45, 75, 90, 802, 24, 2 and 46. This is unsorted list. What we will do here, find the first step is you have to find the largest element among this. Which is the largest element? First step, find the largest element. 802. Largest element you can say as max value. Max value is 802. Okay, and then you find number of digits of this max. How many number of digits are there? 3 digits. Okay, then depends on the number of digits only your algorithm is going to repeat. Let's say you have 3 number of digits, then it will take 3 steps. How many number of steps it will take to sort the algorithm, to sort the array? So it takes only 3 steps. So if you iterate 3 times, one for each significant value, so that your array will be sorted. Now sort the elements based on the units place. Okay, now units place of this is, see here, 6, 2, 4, units place 2, 0, 5, 5, 0. We used to take same size of bin. What is the size of this? 3, 3, 8. So 8 size of bin we used to take. Not 8, sorry. The bin will be 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now you start searching wherever the units place of a number element is 0, just you throw it in this bin. Okay, 170 here. 45 into, because the units place is 5, in this bin. Okay, and 75 also into this bin only. 90 again into this bin. 8 not 2. 2 last element is 2, so into this bin. And 24, 4 here, and 2 means 0 2 again here, and 66 here. Okay, then you again make a one list. This you make it as C. 170, 170, 45, 170, then 90. See here, 170, 90, 802, same, similar. 170, 90, 802, 24, and 45, 75, 66. This is how it will happen. Now in the initial time we have taken units place. Now you consider tens place. See here, 4, 2, this will be 0 2, so it doesn't mean 0, and this is 0, and this is 0, and this is 9, and this is 7. Same, you take a bin, and again from 0 to 9 bins. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 bins you take. 170 means 7th bin, 7. And 90 means 9 digit, so 9. And 802 means 0. Then this is 0 2, so into the same bin. And 2 4, here it is. 45 4, 7 here, and 66 means 6. Okay, see here, 802, then 2, 24, 45, 66, 170, 75, 90. Okay, as I said, this is step 2. We'll be having 3 bins, 3 steps, because the number of digits of maximum number is 3 digits, so that it will take 3 steps. 2 steps we have completed. Now third step. In third step you have to consider hundreds place. 100 place means 0, 0, 1 here. See here, 0, 0, 0, 0, 8 here. Okay, now you take the bins similar. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is at 8th. means 8th bin you have to throw here. And this is 0 to 0th bin 2. Then 24 also 0th bin. Then 45 also 0th bin. 66 also 0th bin because hundreds place is 0. 170 at first bin, this one. And then 75 also 0th bin. 90 also 0th bin. If you merge again, if you make it as one list again, this will be 2, 2. Then 24, 45, 66, 75, 90, then 170, 802. See, the elements of this array are sorted. This is how we perform merge sort. Okay. The time complexity of this is depends on number of digits of max number. Okay. Non-comparative integer sorting algorithm that sorts data with integer keys by grouping the keys by the individual digits which share the same significant position. The time complexity is order of d into n plus b. D is number of digits where. Okay. B is the base of the number, whether which type, whether you are using 10 base or which base you are using. Okay. This is most suitable for large data sets and it is faster than other comparison based sorting algorithms such as quick merge for large data sets. And space complexity of this algorithm is order of n plus b. Thank you everyone.